Okay, so let's start from continuity. So I want to sync with section 5, so I'm going to iterate even if we did some of the part of our slide again. So let me go through briefly about the continuity and the limit of a function. So basically, I want to talk about when the function converges to some certain value, no matter what the function is, even if it's a single variable function or two variable function. So basic idea is I want to move my point in the domain to a certain point. For example, we have a point Q prime here, and I want to move it to closer and closer to Q. And I want to see my function value fq prime to converge to a certain number here. So in this case, the graph is continuous, so we can see that it converges to P. So the problem is, and then we can do the same thing for two variable function. So I want to take a two-dimensional point in two-dimensional region and move that point to near to Q, and I want to see the value of function. So in this case, the value of function is represented in the z-axis of the graph, converged to a certain number. So here the problem is, in the single variable case, you have only two ways of approachment. So you can either approach to Q from the left or right. There are only finite ways to move your point. But in the two variable case, you have infinite number of ways to move your point. So simply checking the left limit and right limit doesn't generalize to the two variable case. So we have to use the notion of epsilon delta statement. So first, let's look at the epsilon delta statement for single variable case. So it says a number L is called the limit of function f at certain point C if it satisfies this statement. So read carefully with me. For every sufficiently small epsilon, which is positive, there exists delta such that if x minus c not equal to 0 but less than delta implies that fx minus L is less than epsilon. So this is a very technical statement. So only mathematicians or math majors will require. But it's what you need to understand is what's the meaning of this epsilon delta statement. It's very simple. So whenever you want to see the value of function, you have to compute that value, and then what you want to compare is the difference between the value of function here and the actual number that you're expecting to converge. So I want these two values to have a small difference. So how small should I change my x from c so that this difference of function f and L is less than epsilon? That's the question. And the statement says I can make this epsilon as small as I want if I choose even smaller delta that guarantees the difference is less than epsilon. So that's the meaning of this. So let me skip this to the case for, in this case, nope, case 2 here. So in the case of two variable function, same applies if I replace the difference as a difference between 2 points. What's the meaning of difference between 2 points? That's the distance between these 2 points. So it says a number L is called the limit of a two variable function fx and y at certain point if it satisfies this statement, which is the same epsilon delta statement formulated slightly differently. For every sufficiently small epsilon, that's the threshold that I want this two value of function, and the L has the difference less than. So then there exists, for every epsilon, there exists even smaller delta such that if I have x comma y satisfying these inequality, then the difference between the function value and L is even less than epsilon. So what is this? This is the distance between point x comma y and a comma b. So if I choose my point close enough to the point a comma b, then I can make the function value small or have closer to L, and the difference is I can make the difference less than epsilon. I can choose arbitrarily epsilon so that if I choose even smaller delta, then I can always make this happen. That's the meaning of the limit. So you can even generalize this. So if you take this as a definition of a limit, you can even generalize to vector valued function. So what is the vector valued function? It's a function that maps a point to a point, right? So if I move my point in the domain to a certain point, what I'm expecting on the codomain is that function value, which is now point, it would closer and closer to certain point in the codomain space. So now I have to compare distance between 2 points in the domain space and codomain space. So it says the following. So if for every epsilon, there exists small delta such that if I choose my point x in the domain space closer to p such that the distance is less than epsilon, then the distance between my codomain point, the point that corresponds to the point x in the domain, which is f of x, is closer to the point q, which I'm expecting that my point, not my function, approaches to. So this distance is less than epsilon. Okay, so that's the meaning of the limit. Now, so it's an interesting thing to see that is sometimes, so when you have a single variable function, you have a divergence. So there are 3 types of divergence. Simply divergence is not convergence, okay? Non-convergence. So in the single variable case, one of the first divergent type is that if the function is not defined, then it's not converging, right? So simply not defined is not a problem. So if you have a function, something like you have a left and right limit not equal, that's one of the divergence. And if your function value is diverging to infinity or negative infinity, that's another type of divergence. Now the problem is there is a same notion of divergence in the 2 variable function case, but when in the single variable case, if you want to check the divergence, you can only check the left hand limit and right limit. That's all, right? But in the 2 variable case, you have to figure out what's going to be for every path that approaches to a certain point. So it's impossible. So it's infinite. So let's look at this example. So if I want to show that this function is diverging at 0, 0, what it means is that I need to know how the function value converges or where the function value approaches when I move my x, y near to 0, 0. So it says, so it's a weird function because if I took this formula only, then it's not defined when x has a same absolute value as y. So I had to set the exception where when x is equal to plus or minus y, then I force this function to be 0. So it's somehow a weird function, and you've probably seen this picture already. So if you try to plot the surface of this function, it looks like this. So you can see that there is a somehow asymptotic plane across this x equals to y line and x equals to minus y line. And across this asymptotic plane, you can see that the surface of the function goes up because the denominator is becoming 0, closer and closer to 0. So it's getting infinite or negative infinite. However, we define the value of function to be 0 along this line, right? So if you choose this path, t comma t, which follows the y equals to x graph, as a path that approaches to 0, 0, then the value of function is always 0, right? So you can see that the limit is 0. But what if I choose different path? So for example, if I choose 0, t, which follows the y-axis to 0, 0, then let's plug that into function, the formula function, to see what the limit is. So let me go back to here. So I'm going to set x equals to 0, y equals to t, and plug in here. So this is not on this exception case. So I have to plug here, right? So 0 plus t squared and 0 minus t squared. T is not 0. So I'm making t closer to 0, not 0. But when t is not 0, this is always minus 1. So if I follow this y-axis path, then I always get minus 1 as the value of function, right? So the limit is minus 1. So already we have two different limits depending on path. So you can see that if it's converging, then if I take any point near 0, 0, the value of function must be close to certain number. But if I choose these paths, it goes closer and closer to 0. But if I choose these paths, then it gets closer and closer to minus 1. So you can see that 0 and minus 1 are, distance. I mean, they are separated apart. So you don't see that there's going to be closer and closer to same number, right? So it's not converging. But you can check with the other path. For example, t comma 0, then it goes to 1. So actually you can make any number as a limit depending on the path in this case. So let's look at another example of divergence. The reason why I'm showing these non-examples, so for example, counterexample of convergence, is that most of the time it's hard to figure out whether it's convergent or divergent by looking at the graph of a function. So you have to look at the formula or some other ways to figure out. So the graph of function looks like this. So this is the formula. So again, we have something weird going on in denominator. It's 0 when x equals to y. So I had to set the exception. So function value is 0 when x equals to y. So therefore, even if you see this steep line, so it's an asymptotic plane across this x equals to y line, the value of function at that line is 0. So you can imagine that there is an invisible line right here. Now, I don't care about the point other than 0, 0. What's going on at 0, 0? Does it look like continuous? Sometimes you can see that, yes, because now, even if it's divergent, so when I approaches to 0, the divergent, the steepness or the size of this divergent number is decreasing to 0, because you can also assume that this is true because you have a second degree polynomial on the top and first degree, the linear term on the bottom. So when you go to 0, 0, then the second degree polynomial dominates or becomes faster to 0 than the first degree polynomial. So you can imagine that maybe the value of function is approaching to 0 when I move my point to 0, 0. But it's not converging. So the picture here doesn't represent the actual shape of this function because when you draw the graph of function, you can only you should only pick the finite number of points in the domain and then plot them together to look like a real graph, but it's not. It's only an approximation of a real graph. So let's think about how we can prove this divergence. It's not convergent. Yes, it's divergent. How we can prove the divergence? The same thing applies here. You need to know in which paths, in which two or more paths, the function value converges to different number. Okay, so if you figured out that every path converges to same number, then you don't prove the divergence. You only get the evidence that it must be convergent. But if you find two different paths which converges to the same point, but the limit is different, then it's the example. It's the proof of divergence. So let's think about this case. Well, it doesn't matter, but y equals to x plus x squared. Or maybe I can, let's see. It's not a good example. So let's see. So x plus okay, well, first of all, let's use this one, y equals to x. So if I follow this path, then the limit is 0. So if it's convergent, then it has a limit. So if I follow the path of y equals to x, that means x is t and y is t. I'm taking t to 0, taking t and t for x and y. So in this case, I'm not using this formula. I'm using this formula because I'm following this path. So it's 0 always. The limit of 0 is 0. So the task is to find, other than this path, that the limit is non-zero. Right? So let's try to think about what other paths can give you a limit which is not 0. So the hint is it should be a curve, not a straight line. So if it's a straight line, for example, y goes to kx, then you always get something second degree and first degree here, so that it always converges to 0. So you need to have certain non-linear curve, so that it converges to 0, but the limit is not 0. So I'll give you a chance to speak to your group member for the first time and discuss about this question, and then we'll discuss together. explain the problem again. Okay, so problem is I want to show that this function is divergent at 0, 0. That's my goal. So in the previous example, what did we do? We select three different, or two different, it's enough, but we select three different paths where each path has different limit. So that proves the divergent. So we want to do the similar here, but the difference is we could have chosen a linear path in this case to show that all limits are different. But here, the linear path doesn't work. So you have to choose non-linear curve, whose limit is non-zero. Because we already showed that if you follow this linear path, then the limit is 0. So all we need is find another path whose limit is not 0 if you follow that path. 몇 조예요? 이름 방금 오신 분 이름 뭐예요? 써라? 그룹 이름을 정하시고 여기다가 크게 쓰세요. 영어로 만드시고 크게 쓰세요. 이렇게 4명 같은 조예요?
왜냐면 약간 캠프라고 되는 혹시
네.
지금 딱 이렇게 했을 때가 y는 x 그래프
네, 네.
지금 이렇게 되는 거는 다 되지 않나요?
그렇죠. 직선은 안 돼요.
직선 y는 x는 직선 아닌가요?
그러니까 yx는 0인데 이제 직선 경로를 다른 직선 경로를 잡으면 항상 0으로 불려만다. 그러니까 증명이 안 된다. 직선으로 또 다른 직선으로 잡으면 어차피 계속 0이 나와서 곡선으로 잡아야 돼. 이거 무슨 뜻이에요?
형 이마트 안 하고 그냥 기본적인
예. 네.
곡선이 들어가야 되는 거예요.
네.
근데 이게 곡선을 어느 곡선이든 넣어도 되는 거예요? 아니면 특정한 곡선을 넣어야 돼요?
특정 곡선을 넣어야 이제 계산을 할 수 있겠죠. 계산을 해서 0이 아닌 걸 보여야 되니까.
아, 그럼 아무 곡선, 그러니까 0이 아닌 곡선을 찾아야 되는 거예요? 그럼 어느 곡선이든 일단 넣어봐도 괜찮은 거예요?
그렇죠. 일단 넣어보고 0이면은 다른 곡선 찾아야 되고 0이 안 되면 이제 찾은 거고. Okay, so any group have any idea? Any group wanna share their idea? No? So anyone wanna try any type of curve? So as I said, you cannot plug in the linear line. So I can show you why. So if it's a linear line, so for example, y equals to kx, then you're plugging this parametric equation. So if k is not 1, then you have to plug in here. So it gives you kt squared 1 minus k absolute value t. So when t goes to 0, this parametric curve approaches to 0, but the limit is also 0. So because we have t squared on the numerator, right? So you cannot use the linear curve to show the divergent. So we have to use the curve. So anyone have any group have any idea about the shape of a curve? Yes. That's good. Yeah, that's actually the correct one. So if I choose y equals to t minus t squared and x equals to t, so that's basically y equals to x minus x squared curve. So then, and also I have to plug that in here. So I get t minus t squared divided by, here now t minus t cancels out. We only have t squared in the denominator. So what do we have? So sorry for bad notes here, but here on the numerator we have t squared minus t cubed over t squared. Now I'm sending t to 0. So which survives on the numerator? Which one survives? Which one dominates? T squared or t cubed? T squared, yes. T cubed is way smaller than t squared. So you can consider t cubed is almost 0. So when t goes to 0, it goes to 1. Okay. So the curve is a parabola, right? So I don't know, but maybe this is the way it converges. But it says if you take this direction or path, then the function value is not going to 0. It actually goes a little bit above 1 here. So it's not reflected in this picture, right? So you can also take any limit. You can make the path so that the function approaches to any number by taking k here, right? Instead of 1, you can take any number k so that the limit is not 1, but any number you want. Is that clear? Okay. All right. So let's talk about the continuity. So this is the punchline. So we so far talk about the limit, but what is the continuity? It's when the limit is equal to the value of function. So if I send my point x to p, if the function value approaches to value of function at p, then it's called continuous. So let's prove the continuity here. So here it's also weird function because we have x in the denominator and x could be 0. So I take that case as an exception and set my function to be 0. And this is the graph. And you can see that it's not a continuous curve that you can imagine because you have infinite number of oscillation as x goes to 0. However, it's called continuous function. It's still continuous. So how do you prove the continuity? It's the same thing. So you have to show that the limit of f of x is 0 when x goes to 0. So in this case, it's a single variable function, so it's a little bit easier than the two variable case. You can only check the left limit or right limit. But now the problem is I don't have a limit for sine 1 over x because I don't know what's happening. So when I move my x to 0, 1 over x is going to infinity, and when I move my number to infinity, it's gonna pass the 2 pi n infinitely many times, so the sine value are oscillating. But what we have here is x multiplied on sine x, and x goes to 0. So therefore, the amplitude of absolute oscillation is going to decrease to 0. So you can say that, okay, I don't know what the limit is, so because it's going to oscillate from minus x to x, but at least I know that it's less than x, or absolute value of x, and bigger than minus absolute value of x when x goes to 0. So what happens when I send my absolute value of x to 0? It's 0. We know obviously that it's 0 because you can draw the nice graph of the function y goes to absolute value of x. It goes to 0 here. So the upper limit of the function approaches to 0. And what about the lower limit? It also approaches to 0 because minus absolute value of x is also continuous at 0. So it also goes to 0. So the lower limit and upper limit both goes to 0. So therefore, on the middle, you can conclude that it also goes to 0. So we know that this is gonna approach to 0. And what's the value of function at 0? We define it to be 0. That's our definition. So it's same as f of 0. So if you took your value of function at 0 as non-zero value like this one, then you can say it's discontinuous, but we gave a nice 0 value to x equals to 0, so it's now continuous. Okay, so that's basically the continuity and discontinuity. I want to move further to the third project now. I want to spare as I said, spare 1 week before our final or mid presentation in order to give the feedback of your project. So before I move on to the next slide, is there any question? No? Okay, so let's talk about our third project. So it's basically about the graphing function. However, when you draw the graph of single variable function and two variable function, there are already a function implemented in the matplotlib. So what we're going, and also there are many other types of graph that you can draw using the function implemented in the same library. But we're gonna first discuss about what are the types of graphs that we can visualize for various types of function. So one type of graph is the parametric curve. So it's a function having one input variable and several other output variable. So two or more output variable. So in this case, we have t, a single input variable, and two output variable, which is a formulated in t squared and t cubed. So in principle, you need three variable, and three variable requires three-dimensional space to fully draw its graph. For example, if you have a two-variable function z equals f of x, y, then you can draw that surface as a graph of function in the three-dimensional space. The same thing applies to here if you're strictly speaking about the graph of this function. However, when you have this type of function, we're not going to draw in a three-dimensional space. Instead, we're going to draw in a two-dimensional space as if t is a time, and we're moving the point t squared comma t cubed inside of this two-dimensional plane over the time. So you can see that when t is equals to 1, let's say minus 1, it starts from here because the point is 1 comma minus 1. And when t goes to 0, it moves along this curve. When t goes to 0, you reach to this point. And then when t moves up to 1, it moves up to this point, right? So this is how you draw the graph. So basically, when you try to draw such graph, what you need is not trying to plot the range of t, but only plot the range of x and y. So you can do the same thing for three-dimensional curve. Here we have one input variable, three output variable, formulated in this way. So it's I think basically figure 8 knot. And you can see that the curve inside of this three-dimensional space are knotted together. So you cannot untangle this one. So you can see that in the code, I made a 3D figure, and then here I had to equally partition this range of t from 0 to 2 pi, but what I actually put into the plot is the list of or array of x and y and z value given by the array of t, so x and y and z, based on the formula I have here, and plot x comma y comma z as a three-dimensional point, list of three-dimensional points, then I get this plot. So I'm not going to do this again because it's already here. So let's make let's try to think about other types of graph. So you probably have seen this terminology in the engineering mathematics. So if you have a function whose value of function is represented as a y, the variable y, which depends on n variable from x1 to xn, but you don't have an explicit formula of y in terms of these variable x1 to xn. Instead, let's say you have an equation altogether. So for example, if you have this equation, you can imagine that this y value is dependent on the value of x. You cannot independently choose x and y because it has to satisfy this single equation. So you can imagine that this x value somehow determines the y value, but not uniquely, but in a sense. But however, it's somehow it determines the y value. So this is called the implicit function. So what's the function here? The function is a function about y, but it's given in the implicit way. So how do we find out the function or graph of the function here? So we need to parameterize the x and y in terms of other parameter, so in this case t, so that this parameterized curve, parameterized function satisfies this implicit equation. So here I use the hyperbolic cosine, hyperbolic sine. So you have to remember this formula. So its hyperbolic cosine is sum of two exponential with a different exponent here, divided by 2, and sine is the negatives. Then you can draw a function here. It's actually a hyperbola. It's same curve as y equals to 1, but it's rotated 45 degrees. The reason why it's rotated is you can split this equation into factor of x minus y and y plus x plus y, and you can have a linear transformation from x comma y to x minus y comma x plus y. That's a 45-degree rotation. And you can also represent a graph when the function is given in the polar coordinate. So you probably know what polar coordinate is. It's a coordinate given by the distance from the origin, which is r, and the angle between the positive x-axis and the line connecting a point and the origin, theta. So x and y are given by this formula. And for example, if you have the polar curve, meaning that you're looking at a point, but the location of point is represented by r and theta, and this is the equation that determines this r and theta. You can see that this r is also a function of theta, but implicit way, because we have a square here. But when you have such curve, it's easier to find its parametric function, because it simply says, okay, you have the radius, the distance between the origin to the point, as a square root of sine 2 theta. If the theta, or if the sine value is negative, it means that there's no such point. So it's impossible. So when the theta 2 theta ranges on an interval where the sine values are negative, you can disregard this point. And x theta now therefore is given by r cosine theta. R is given by this, and y is given by this. So we only draw the function or point or the curve of the parametric function like this one in two distinct intervals from 0 to 2 pi, pi over 2 and pi to 3 pi over 2. And because of periodicity, we have an iteration between, we have a periodic movement around this figure 8 curve here. So I think it starts from here, yes, and then it goes move up to, or maybe here, whatever, and move up to here. So that's one way you can draw the graph. So let's generalize a little bit more. So far we only draw the curve. Now we want to draw the surface. So how do you draw the surface? Surface is two-dimensional, obviously, so you need two variables, right? So curve is one-dimensional, so you need only one parameter, t. So but in the surface, you need two parameters, u and v. So u and v is just arbitrary variable symbol. You can replace it with any other variable, but I choose u and v because I want to choose x, y, z for the codomain space variable. Okay, so the simplest possible equation for the parametric surface is plane. For example, if I choose z equals to 0, that's a parametric surface. It means that whatever your xy is, the z value is always 0. So you can choose any xy, but z coordinate must be 0 in your space. That's the xy plane, right, in three-dimensional space. So let's generalize a little bit more. If the point satisfies this equation, let's see what it means. So here x1, y1, z1s are constants. Okay, so these are constants. I took the x1, xy, z1 from the point x, y, z. So it means I took the position vector from x1, y1, z1 to x, y, z, right? I took the position vector, and these are the coordinate of this position vector. And I take the inner product, that position vector, with another three-dimensional vector whose coordinates are A, B, C. So this is basically what it is. So we have A, B, C, inner product with Px. Sorry, so in this case, X, let's see, P1P. So P, I took this X, Y, Z. So P1 is X1, Y1, Z1. So this is fixed. Okay. So, and P is the point considered as an arbitrary point on the plane. Okay, so this is the same equation. So it's a rephrase of the equation here. So what does that mean? So ABC is a three-dimensional vector. Let's say this is our ABC. And P and P1 are somewhere here. And I took the position vector from P1 to P. So it says these two vectors are inner product to 0. It means they are perpendicular, right? So if I take any point P with this property, then it means that I'm taking a point P on a plane which passes through P1 and perpendicular to ABC vector. Okay? So in other words, if you take point P1 and some three-dimensional vector, which is non-zero vector obviously, then you can always determine a three-dimensional plane, a two-dimensional plane on three-dimensional space. So you can do the similar thing with another set of data or information. So if you have, let's see, a point P1, whose coordinate is P, x1, y1, and z1, and if you know that there are information about two vectors, v1 and v2, which is parallel to the plane, then you can find the perpendicular vector ABC by taking an inner product between v1 and v2. You can switch the order of cross product here. Sorry, did I say inner product? It's a cross product. So then you can use the same vector ABC here to get the equation of the two-dimensional plane in three-dimensional space. So here's how you draw the graph. So let's see, here we have two vectors which are supposed to be parallel to the plane, and we're assuming that the plane passes this three-dimensional point. So you can find your equation. Let's try to find the equation first and then try to explain the equation, the code here. So finding equation does not automatically give you the way to draw the graph. So here, the way I draw the graph is a little bit different. So let's try to find the equation of x plus z plus something. So here, something here equals to 0. So find out what the values goes here, and then we'll discuss about the code. So it's now time to discuss with your group member. So you can use the formula I just put up in the slide here to figure out the equation of the plane satisfying this condition. 다음 수업 시간에 종이를 좀 갖다 드릴까요? 종이에다가 좀 크게 놓고 친구들이랑 좀 쓰면서 보게. Does everyone remember how to get the cross product? Forgot already? Probably forgot. That's the that's a negative side of the lecture. So if you listen the lecture, you always forget. So that's why you have to put your hands in. So when you try to get the cross product, you have to find the determinant of 3 by 3 matrix like this, right? So how do you take the the determinant? So here is a positive and here is the negative. So it's a negative and positive. So when you take the yellow lines, it's a positive sign, and the red lines are negative sign. 응? 그 다음에 어떻게 해요? 곱하는 거잖아요. 이거 하고 있는 여기? 다음 시간에 종이를 좀 가져올게요. 이게 요즘 태블릿을 언제부터 썼어요? 고등학교 때부터? 그 전에는 종이에 썼잖아요. 요즘 애들은 모르겠어요. 요즘 애들은 초등학교 때부터 태블릿에 쓰니까 그게 맞춰져 있을지 모르겠는데 이게 태블릿에 끄적거리면은 생각이 좀 잠기는 것 같거든요. 제가 느끼긴 좀 그렇거든요. 그러니까 이미 알고 있으면 태블릿에 쓰면 괜찮은데 그냥 이렇게 막 써보기에는 좀 좋은 것 같지 않아서 한번 가져와 볼게요. 어떤지 한번 보세요. 그러니까 제가 가져올 종이가 A4가 아니고 큰 종이거든요. 여기다가 크게 써보세요. 이렇게 조그맣게 말고 크게 그냥 진짜 크게 그렇게 한번 써보면은 좀 사고가 좋아질 거예요. Okay, so what's the cross product? Can anyone call the component of cross product? V1 cross V2 is, can anyone done the calculation? Any group? I'll give you more time. 조언들 알아요? 알아요? 아는 친구들이요?
아는 친구들인데.
아니, 그러니까 아는 친구들이요?
네, 아는 친구.
아,
아는가?
그럼 조 이름을 그냥 본인이 정하세요. 뭐 하고 싶어요?
민중.
고민 중이에요? 아, 오늘 안 정해도 되니까 뭐 너무 급하게 안 해도 되고 대신에 이제 정했으면 크게 쓰세요. 네, 좀 그게 잘 보이게. 계산했어요? 머릿속으로 하고 있어?
근데 이게 잘 안 되네.
뭔가를 계속 써야 되지 않아요? 타이핑이라도 해야 되지 않을까? 머릿속으로 칠 때.
으로 계산하기.
Did any group calculated the cross product? Yes. What is it? -1? 3? Is it right? Does it seem right? Okay. So if I have the cross product, that's my vector perpendicular to the plane. So how do I get the equation? So you take the position vector from the fixed point. So my position vector is this: x minus 1, y minus 2, z plus 1, and you take the inner product between these two vectors equals 0. That's the equation that x, y, z satisfy. So this is minus x minus 1 minus y minus 2 plus 3z plus 1. So let's see. 3z. So I'm going to make it into an explicit formula for z. 3z, let me do it slowly. Minus x minus y plus 3z and plus 1 plus 2 plus 3. Okay, so it's 3z equal to x plus y minus 6. So z is equals to 1 over 3x 1 over 3y minus 2. So that's your equation of a plane. It's the same equation as here. So you can draw the graph of graph of this plane as if it's a two variable function, the graph of two variable function. Or you can think about what I did here. So here, what I did is basically I took my UV parameter from -1 to 1 and took the mesh grid and then set my mesh grid of x, y, z coordinate in these ways. Oh, I think I forgot to. I think I forgot to shift this part. Okay. So anyway, I can fix it together. But why? So you can see that this is not the same, this is not the same way we formulated our function, formulated our plane. So if I use this equation as an equation of two-barrel function as well as the equation for the plane, then x and y serves as a parameter. Okay, so x and y range from -1 to 1, and then z is somehow 1 over 3 times the x coordinate of the grid point and 1 over 3 times the y coordinate of the grid point. But this equation is nothing similar to that. X and y are somehow the equation of a parameter u and v, and z is a parameter of v. So what's going on here? So there are another way of parameterize the plane. So this is one way. This is somehow it's a parameterization of the plane as if you're looking at the two-dimensional function. But think about this case. So maybe I think I should pop up another. So let's use this one. So think about this way. I have a plane and I have a point that the plane passes through. I want to figure out all the points. I want to parameterize all the points in this plane. The way I can do that is if I know two vector lying on the plane, which is parallel to the plane. So then I can set my grid line parallel to these two vector, and then I can move v1 vector in certain degree and in the v1 direction by certain degree and certain amount, and v2 direction by certain amount to to locate my point in the plane. So if I take, let's see, u1 or u times of v1 vector, and then if I take v times v2 vector, sorry for having the same symbol v, but here u and v are considered as scalar. v1, v2 are considered as vector. That's why I put the arrow sign above. So v1 over v2. So then I can map my point on the plane right here. So this is u times v1 plus v times v2. And then I shouldn't forget about this P1. So plus P1. Okay? So let's plug in the numbers here. So we have U times V1 is, I think it's better to put it here. So let me write it here. So U times 2 minus 1, 0 plus V times 1, 0, 1 plus P, 1, 2 minus 1. So that's going to be my coordinate of point on the plane. So let's combine this all together, which is 2u plus v plus 1 minus u. Now v is, there's no v because it's multiplied with 0. And the third one, z coordinate has no u, v minus 1, right? So this is my x, y, z coordinate of point on the plane. So that's what I did here. So as I said, I forgot to shift the point to by this much. So I have to add plus 1 and add plus 2 and minus 1 here. So then I get the same plane, same equation of the plane, but parameterized differently. So maybe we can do this together just to check why this is true. So I'm going to open up the Colab here. So today's Colab is this one. So as I said, we're going to use the matplotlib and numpy always. So I'm going to import everything. And then I'm going to use my UV as the parameter. And I'm going to take a mesh grid of these two. And then my X, Y, and Z is going to be 2UU plus VV plus 1 for X minus UU plus 2 for Y and V minus 1 for Z. Then I'm going to plot this. So first, I think I should PLT figure add subplot, and then I don't need the color map. So you will get the same figure, but that's not the same figure in the slide, by the way. In the slide I forget to shift the plane by amount of the point P. So maybe I can set aspect equal. Right. Now I get the same similar shape. So so instead, now let me give you another way of drawing this. So instead of doing it one time, so I'm going to plot differently. So let's see. So I'm going to use x and y to be the linspace minus 1 to 1. So I'm going to use the two variable equation of z, and xx and yy is the mesh grid of x and y. So when I use the two variable explicit equation for z, x and y is already the parameter of the surface. So xx and yy are given by the mesh grid of x and y, and I only need z to be 1/3 of xx plus 1/3 of yy plus minus 2. So then I can plot surface x and y and z and set the aspect equal. You get the same figure. But now, oh, by the way, so it's, sorry, so this is not the string. I think it's just a number. Yeah. So 1-to-1 meaning that it's a 1 row, 2 column figure with the first figure, and 1-to-2 means that it's a 1 row, 2 figure with the, and we are looking at the second figure. The last 2 means that it's the number of figure, the index of the figure that you're looking at. So sorry, so it has to be 2-1. Sorry, 1-2. That's right, 1-2. Why does it look like this one? Y-2-2. Oh, wait. Hmm? Okay, I don't know why it's showing me a column figure, but let me try out with this one. Maybe it shows me, it's the same thing here. I don't know why. And also I don't know why it's a curved figure. Something went wrong in here. But anyway, let me figure out why the second figure looks like a curve instead of a plane. So here we have xy from -1 to 1, xx, yy to be the mesh grid of x and y. That's right. And then z is 1/3 xx plus 1/3 yy minus 2. And plot xx, yy, z. That looks weird. Yes. Ah, okay. So you have a okay, double asterisk. Okay, now you have a surface. Okay, plane. Okay. Is it the same plane? Yeah, it should be the same plane. If I didn't confuse with the computation. So it's the same plane, but you're looking at a different perspective. The first one is you parameterize u and v. That gives you the scale of each vector, v1 and v2. The second one, you're looking as if you're looking at from the top. So you parameterize the surface in terms of x and y, and you only measure the height of the point on the plane. So that's why it looks different. But I think also because of yeah, so it's basically the same, but looking at different. You can see that the domain x and y range are different, right? So here range from -1 to 1, obviously, but here it ranges from different range. So you can see why it's different. So, but you can see that their slope, in some sense, the slope of plane are the same. Just you chop up the different part of the infinite plane, and that's why it seems different. But they are actually the same plane. Okay, I'll put it here and okay, I hope I was thinking if I could go to the contour plot part. Okay, I don't want to rush, so let's try to practice this one, and then let's do the contour plot next time. So here are the various surfaces you can try to visualize. The helicoid, which one do you think is a helicoid among these four? So helicoid somehow reminds you of a word helicopter, right? Helicopter rotates. So which one rotates? So this one looks like it rotates. So this is a helicoid. The helicoid is parameterized by these equations. So u, v are ranging in here. Of course, I cannot draw infinite interval. So you have to restrict the interval from, in this case, 0 to 2 pi, or 4 pi, I think. Anyway, and v only range from 0 to 2 pi because v goes into the sine and cosine. So there's no meaning of ranging v to infinite because it's going to periodically iterate. And Yeah. Oh, by the way, so Z is 0 to 2 pi. Z gives you the height. So U gives you the width of your wing of this helicoid here. Let's try to draw this one, and then let's draw another one too. So here I already imported the NumPy and matplotlib, so I can simply take U and V to, oh, so it's a different range. So U is NumPy from, let's see, 0 to 1, I think. So U is originally minus infinity to infinity, but I restricted the domain from 0 to 1. And V is 0 to 2 pi. And mesh grid and XX, oh, so here it's hyperbolic, what was it? Sorry, hyperbolic sine. UU times cosine V, VV, and sine and cosine, and then surface plot. Huh? Sorry, it's not U, it's V. Yep, so you have it here. So you can increase the range of V to, I think, maybe 6 to get a longer helicoid. So let's see. I'm going to set the aspect ratio equal. To see that helicoid is actually an helicoid. So if you're done with the helicoid, you can try catenoid. And well, I didn't put other parametric equations. So try out the equation for catenoid, and then the figures below, helicoid and catenoids are torus. The left one is torus, and the right one was the Möbius band. So you can try find what's the equation for the torus and the Möbius band, and then try to figure out how to draw this as if in the figure. Try the catenoid. Try draw the catenoid. Is that the figure? But that doesn't look like a catenoid, helicoid. What went wrong? Oh, you put the VV here. 무스타파가 무슨 뜻이에요? 네?
동반 친구 이름.
그 저기 새내기 클래스. 근데 여기 없잖아.
학교.
네?
학교를 바꿔가지고.
없다고요 지금? 떠났어요? 아, 벌써? 입학한 지 얼마 안 됐는데? 그러면 이제 딴 데도 붙어서 간 거예요? 바뀌었다는 게 무슨 말이에요? 아, 하긴. 근데 새내기 클래스까지 하고 그렇게 뒤에 옮겨도 되나? 여기까지 등록 다 한 거잖아요. 되게 신기하네.
케이스.
친구를 그리워하는 마음을 쓴 거예요. 다 했어요? 그려봤어요? 한번 해보세요. 콜앱 들어가서 해보세요. 저 카테노이드도 그려봤어요?
아직
해보세요. 그래. 잘 하셨으니까.